So today I will present you the laboratory work number 4 uh, about NP complete class problems and what you need to present in the report and how your laboratory work should look like. Now the sheet that you have in Moodle, so the aim of the work is solving one of the problems belonging to NP complete class. You can see that there are 7 problems. You can choose which one you like, and the task is highlighted here, so you have to develop the program and solve it using 2 different computers. Describe the parameters of the computers and compare which did faster. Of course, the computer with higher parameters will be faster. Then theoretically evaluate the complexity, experimentally evaluate the complexity, and check if they match. And then complete runtime function, compare runtime function with the runtime of laboratory work number 2, where you were searching for the shortest path. Now I will describe 2 problems. These are the works done by students, so your colleagues, so 1 year or 2 years ago. So the first problem is traveling salesman problem. On the left you can see the code. I will not go deeper into the code because it's your job to go deeper into the code. So I will just describe how that laboratory should look like. Laboratory work description should look like. So at first you need to write the code and describe the computer characteristics. So here we have 2 different computers with parameters that are quite a bit different, but they make the difference in the end. So the code is on the left, but it's your job to write the code here, and the originality of the work will be evaluated. So you can, of course, can look at this code and but just don't use the same. Okay, now so the task is to evaluate the runtime, the time for this NP complete problem of traveling salesman using these 2 computers. So you can see in the table here that there were selected 8 to 12 cities, and you can see that how the complexity increases with increasing the number of cities. So it is the table with computer 1 and computer 2. So now the task number 2, theoretical complexity. So in this case, for students, it is difficult to evaluate the theoretical complexity, and this is because it needs a lot of practice to exactly know what is the complexity. So I have added a slide, the further slide. So as you can see, NP problems, they are non-polynomial problems. So it means they cannot be solved in polynomial time. So the complexity cannot be polynomial if you solve them. In some cases, in very rare cases, it can be exponential, since exponential, it is, as you can see, polynomial. It is here. So exponential, it is here. So exponential is, as a function, it goes faster. But if we compare to the algorithms, we say the word slower because it takes much more time. So then the algorithm is slower. So it takes much more time to solve Yes, if we compare the exponential to polynomial. But as a function, it grows faster. So we have a polynomial here. Exponential is much faster than polynomial. So NP can be solved in polynomial, so they can be solved in exponential in rare cases, but usually they are here, and this is factorial. It is factorial dependent. It can be even more difficult. It can be n times n factorial. It can be n squared times n factorial. But usually because NP complete problems are very difficult, so it takes factorial or even n times factorial or n squared times factorial or something more difficult. But usually we refer to the let's say to the highest order. It would be factorial, so we describe it as n factorial. So now thinking about the code, when you have the code for students to describe the complexity using the code, as I've mentioned, it is difficult because it requires practice. But usually when you write the code, you follow some kind of internet page or some kind of example. So usually the complexity is given, so you can try to copy that complexity and just check using your knowledge if it is the same or not the same. But it's not very I allow you not to be very specific because it takes much practice, and for bachelor students it is difficult. So just try to evaluate this theoretical complexity as you can. Now experimental complexity. So using this using the approach that I give you here. So in this case, the complexity, it is also factorial. So we can say that, and you also can follow this example for your task, that using computer 1 and computer 2, you can see that computer 2 is slower because it takes much time. It increases faster with increasing number of cities. And the dependence is factorial because, as you can see in the table, when you increase the number of cities by 1, and then in computer number 1, it increases the complexity increases from 3 to 48, as you can see here, from 3 to 48, and here it increases from 8 to 109. Yes, so it increases drastically. So this increment is much faster, as you can see. Also here, this increment occurs very sharp. It goes like this and then occurs very sharp. So this is the example of factorial increase. So this factorial increase, you can see this curve. This is factorial increase, much sharper than the exponential increase. Now, comparison with Dijkstra algorithm from laboratory work 2. The student used Dijkstra algorithm. So you can see that it has the number of vertices, let's say here 200, here it is 100, and when it is from 0 to 100, the time necessary for the time was very low, so it was less than 0.0, it may be 0.0, 2 zeros and 1 maybe, because this is 0.025, so it was close to 0. So when he was trying to compare the cities from 0 to 10, but in this case, in in traveling salesman problems, as you can see, when he was using cities, let's say 12 cities, so the time required was around 50 seconds and around 100 seconds for 12. And when you can see here, so for, let's say, for 100 cities, here the time was less than 0.025 seconds. So you see how much faster and how much faster the Dijkstra algorithm was performed, and because the algorithm is easier. Now the next example that I have here is Hamilton cycle, and you can see the graph. The graph was done with different number of vertices, as you can see on the right, and the time was evaluated. So this is another example. Now the code you can see on the left, and you can just follow this code if you choose the same task, but just don't make copy of this. And the parameters of the first computer and the parameters of the second computer. And the second computer, as you can see, they have the parameters that differ more than in the previous case. Now, if we check the time for the task to be completed necessary for these both computers, so we can see that in this case the parameters here, we can see that the number of frequency in the first computer is less gigahertz than in the second, but random access memory is twice higher than in the second computer, and the outcome is that they operate almost in the same way. And the most important thing is that 45 number of vertices is 45, and when you increase by 255, so from 136 seconds, it increases drastically to 5,400 seconds, and this is something like, if you divide it by 60 seconds, it would be about 90 minutes. You would get about 90 minutes. This is 1.5 hours. And as you can see, the function increases drastically. Small increase in X gives drastic increase in Y. And it increases much more faster than exponential. So this is again the example of factorial function. And as you know, NP problems cannot be completed in polynomial time. They are completed in times in time that it's much longer than polynomial, exponential. So usually it is factorial or even worse. Yes. Now the theoretical complexity, as I said, Hamilton cycle has factorial, and experimental complexity, as I've just told you, it is also factorial, so we can see from the curves. So in this case, there is no, the student missed the comparison with lab work number 2, but you can add this, because at that time we were not doing comparisons with lab work number 2, but you need to add this. So so these were the examples, and I think you know the task, and if you have some questions, just write me to Outlook, and good luck.